In this module, we are going to learn about the Metropolis-Hastings algorithm and the different steps of the Metropolis-Hastings algorithms and different issues to implement the Metropolis-Hastings algorithm in R, and then random walk Metropolis-Hastings algorithm and its implementations, and then finally we will do a simulation study to see how the Metropolis-Hastings algorithm can be implemented, and different codes that we are going to generate that may not be readily available defined code in R. We may have to generate our own code most of the times that we are going to do, and that might help you to develop your skill to implement Metropolis-Hastings algorithms. We'll talk a little bit about the convergence and the diagnostics of Metropolis-Hastings algorithm. In this module, we'll learn how to implement the Metropolis-Hastings algorithm in R under the MCMC setup. And before that, let's recall the Metropolis-Hastings algorithm. We're given a probability density pi called the target, defined on a state space chi, and computable up to a multiplying constant. Then pi x is proportional to pi curl x. The Metropolis-Hastings algorithm, named after Metropolis et al. And Hastings, proposed a generic way to construct a Markov chain on chi that is ergodic and stationary with respect to pi. The Metropolis-Hastings algorithm is the workhorse for MCMC methods for its simplicity and its versatility. Unlike acceptance and rejection algorithm, Markov chain construct a progressive picture of target distribution, proceeding by local exploration of the state space chi until all the regions of interest have been uncovered. The Markov chain return by MH method, say x1, x2 or xt, is such that xt is converging to pi. This means that the chain can be considered as a sample through a dependent sample and approximately distributed from pi. Due to Markovian nature of simulation, the first values are highly dependent on the starting values x1 and usually removed from the sample as burn-in or warm-up. If the Markov chain is ergodic, that is, forget about its starting value, the empirical average that eta t hat h equals to 1 by t, t equals to 1 to t, h xt converges almost sure to eta h, no matter what the starting value is. The Metropolis-Hastings algorithm. The Metropolis-Hastings algorithm associated with a target density pi requires the choice of a conditional density q, also called proposal or candidate kernel. The transition from the value of Markov chain xt at time t and its value at time t plus 1 proceeds via following transition steps. Given xt equals to small xt, generate yt from qyxt, and then xt equals to yt with probability rho xt comma yt and small xt with probability 1 minus rho xt comma yt, where rho xy is equals to minimum of this expression. In practice, the performances of algorithm are obviously highly dependent on the choices of the candidate density. We'll start with an example of say our target density is a perturbed version of normal 0 1 density. Phi naught is actually in this form. Say pi square x is the sine square x into sine square 2x into phi x. Phi x is a normal 0 1, and our proposal is, say, assume a uniform distribution from u x minus alpha x plus alpha kernel. Then q becomes qy given x is this expression 1 by 2 alpha into I x minus alpha to x plus alpha into of y. Implementing this algorithm is straightforward. Two functions to define are target and the tangent. The target function can be defined in this form. Say target equals to function x and then sine x square into sine 2x square into d norm x, and then metropolis function is say x alpha equals to 1, then very simple y equals to draw a uniform random variable from x minus alpha to x plus alpha, and then if uniform 1 is greater than the ratio of target y by target x, then y equals to x and return y. Otherwise, the y would be as remain same of the previous state. So this is the two functions that I define. One is this the tangent step, another is the target density. So now let's set n equals to 10,000 and x equals to say the 3.14 replicate the 3.14 for n times, and for I equals to 2 to n, the metropolis steps you can say xt equals to metropolis xt minus 1, and normal target is another function. Let's define is function of x target x by integrate normal target minus 3 to 3 is just a constant factor. The integrate normal integrate target minus 3 to plus $3 value will give the normalized constant value to compare the fit generated by the metropolis. So now draw the histogram of x that here, and then of n class, say number of class is 200, and then get the curve of normal target density, that is norm target, that has been defined by this function. Then you can see it's quite fair, quite good fitting over here. When working with a Metropolis-Hastings algorithm, the generic nature of algorithm is as much an hindrance as a blessing, in that the principle remains valid for almost every choices of proposal Q, but the convergence and convergence rate depends on the choices of the proposal. The closer proposal will give you quicker convergence. As an illustration, let's choose 3 different values of alpha. Say alpha equals to 0.3, 3 and 30. Say n equals to 10 to the power 4, then x generated matrix of 3.14 n by 3 matrix, then alpha equals to 0.3, 3 and 30. Then k equals to 1, 2, 3. For different alpha, we'll generate the Metropolis-Hastings algorithm. And then we'll do the ACF plot separately for 3 different Metropolis sample that generated for 3 different choices of alpha. And that is coming, this looks like this. The figure showed the alpha equals to 3 should be preferred to the other 2 values, as autocorrelation died much sooner than other 2. This indicates proposal density plays a vital role in rate of convergence. Now we'll move on random walk image algorithm. The generic version of Metropolis-Hastings algorithm is the random walk Metropolis-Hastings algorithm, which exploits as little as possible knowledge about the target distribution, proceeding instead in a local, if often myopic manner. To achieve this, the proposal distribution Q aims at a local exploration of neighborhood of the current value of Markov chain, that is simulating the proposed value yt as yt equals to xt plus epsilon t, while epsilon t is a random noise with distribution say g. It could be uniform or normal distribution. When g is symmetric, the acceptance probability of MH algorithm becomes rho xy equals to minimum of pi square y by pi square x comma 1, and choice of Gaussian density as the G provides the ideal acceptance rate. Let's assume a linear relationship between the predictor and the response variable. So we take a linear model and add some noise. The true A equals to 5, true B equals to 0, true SD equals to 10, sample size equals to 31, X equals to is the independent variable X is a sequence from minus sample size minus 1 by 2 to sample size minus 1 by 2, and Y equals to, actually it is AX plus B plus normal 0 SD. So true A into X plus true beta plus normal, and n is sample size mean 0 and standard deviation true. So this way you can generate the Y, and this plot looks like straightforward, I mean looks like a linear association the way I assumed. For estimating the parameter in a Bayesian analysis, we need to derive the likelihood function for the model that we want to fit. So given our linear model y equals to alpha plus beta x plus e normal 0 sigma takes the parameter alpha, beta and sigma and as input, and we have to return the probability of obtaining the test data above under this model. So first let's define the likelihood by this function. Say I am just passing the parameter, the param is a argument, through that I am passing all the parameters. Say A equals to param 1, A equals to param 2, SD equals to B equals to param 2 and SD equals to param 3, and predictor is the pred A into X plus B, and the single likelihood D norm Y mean equals to pred, SD equals to SD and log equals to 2 log likelihood will return, and then the sum of log likelihood is this and return value is the sum of this expression, and that will give you the likelihood value. The log likelihood profile of the slope parameters, if I see the values of, if varies the slope parameter, how the likelihood varies. So slope values, say I am just passing the values of x and then return likelihood Cx, true B and true SD. Then the slope likelihood, say A Laplace sequence from 3 to 7 by 0.05 and slope values, comma slope values. Then the plot this sequence from 3 to 7 by 0.05 and the slope likelihoods that calculated by this expression and type L, and that will show how the likelihood varies over the different values of slope parameter. Prior and posterior distribution. As a second step, as always in Bayesian statistics, we have to specify a prior distribution for each parameter. To make it easy, we use uniform distribution and normal distribution for all three parameters. I mean, the prior can be defined as a prior distribution. So prior param 1, param 2 and param 3, and then a priori to D unif, and the second one is the D norm, and third one is D is from uniform distributions, and return the A prior plus B prior plus SD prior. And the posterior distribution is, say, return the log likelihood of parameter plus prior parameters out of this, and that will give you the posterior distribution density. And now we have the prior and the posterior distribution, and the proposal function can be developed as the proposal density is returned normal 3 mean param and SD equals to 0.1, 0.5, 0.3. So this is the proposal function. Now here I am developing a metropolis algorithm again, that function start value and number of iterations. The chain equals to array dimension, C iteration plus 1, 3, then chain 1 start value, then using a for loop, proposal equals to proposal function, we get the proposal, and then probable that expression of e to the power of posterior proposal minus posterior chain, and then if uniform this less than this, then chain the next value is the proposal, else it is the previous value, and return the chain. That's the normal algorithm that I mentioned before. And then start value is say 4, 0 and 10. Call the Metropolis algorithm start value and 10,000, burn in say 5,000, then acceptance is 1 minus mean duplicate chain minus this. So this will give you the acceptance rate. Some notes. So working with the logarithms of the posterior might be a bit confusing at first, but in particular when you look at the line where the acceptance probability is calculated, say probability AB equals to this, actually understand by why we do this. Note that the P1 by P2 is actually e to the power log P1 minus log P2. So the first step of the algorithm may be biased by the initial value and are therefore usually discard the for further analysis. This is called burn-in. And interesting output to look at this, the acceptance rate. How often was a proposal rejected by Metropolis Hastings algorithm, Metropolis acceptance criteria? So that can be stored and can be displayed. The acceptance rate can be influenced by proposal function mentioned earlier. Generally, the closer the proposal are, the larger the acceptance rate. Very high acceptance rates, however, are usually not beneficial. This means that the algorithm is staying at the same point, which results in a suboptimal probing of parameter space. The acceptance rate between 20% to 30% are optimal for typical applications. So here is one example that I am using for the plots, actually some diagnostics of the previous example. That if you these plots, these codes will give these plots, that the posterior, then posterior A, posterior B and posterior SD, and then finally the red value is actually it will show the how it's generating, whether this is the red value is actually the true value, then how the different values as generated for that parameter are distributed over the true value, and these red lines for all the cases are actually the true value. So this is all about the Metropolis algorithm. Markup might be it is very important sampling technique for Markup chain Monte Carlo methods. We have learned different challenges implementing Metropolis Hastings algorithm in R, and what are the different aspects that we need to look into before we implement the Metropolis Hastings algorithms, how important the proposal density is, how the convergence can be controlled by different choices of Metropolis Hastings parameters. These particular presentations, I guess, might be very helpful to understand how to implement the Metropolis Hastings algorithm successfully in not only in R but also in any statistical software.